Hello everyone, this is part 2 of simple linear regression in econometrics. And in this video, I will actually calculate the equation of the fitted line that minimizes the sum of square prediction mistakes. Let's continue from part 1, starting from this equation where yi, which is the exam score for student I, is explained by xi, which in our example is the hours studied for student I. If you remember, this portion in brackets represents a straight line with b0 being the intercept and b1 being the slope of the line. And the vertical difference between the straight line and the exam score for student I, we call it the prediction mistake corresponding to student I. Finally, the subscript I runs from 1 through n, where n equals 30 in our example because we have 30 students or observations in our data. Now, given our 30 data points, the goal is to find an equation of a fitted line or solve for b0 and b1 of a fitted line such that the sum of square prediction mistakes is minimized. So what that means is that we're going to be minimizing this term with respect to b0 and b1. And by looking at this equation, we know that the minimization problem is the same as this minimization problem at the bottom. Okay, then now I'm going to bring up the problem to the top, and in order to find the minimum, we have to differentiate the term using b0 and b1 and set them equal to 0. So then with respect to b0, the first order condition is this one, and with respect to b1, the first order condition is going to be this term at the bottom. In case you're wondering, the term we're trying to minimize, which is the sum of square prediction mistakes, is strictly convex. So we're going to get a minimum and not a maximum if we satisfy the two first order conditions. Let's first start with the FOC for the B0. So I'll bring this equation to the top like this. And before moving on, if you're not comfortable working with summations, you can take a look at one of my videos which goes over some of the properties involving summations. The link is down below, so you can just click on it. Okay, coming back to our problem, after differentiating with respect to b0, we're going to get this condition or equation, and this is going to be the same as this equation if we divide both sides by -2. From here, we can bring in the summations like this, and now I'm going to bring up the equation to the top like this. And from here, we see that the term involving b0 is all by itself, so it's going to be easy to solve for b0 now. With a bit of algebra, you end up with an equation at the bottom. I've shown each step of the way, so you can pause the video if you want, but the bottom line is that b0 equals mean of y minus b1 times mean of x. Yeah, so to explain about the notations, y bar and x bar, they represent the means or simple averages of y and x, respectively. Now, we can work with the first order condition for b1. Differentiating the term with respect to b1, we get this equation, which then equals this equation. And here, we want to plug in for b0 that we already solved for in the previous steps. Doing so is going to give us this equation at the bottom. And now we can solve for b1 without worrying about b0. Now I'm going to bring the equation at the bottom to the top of the page. And after shuffling things around a little bit, you're going to get to the equation at the bottom of this page. You can pause the video and check each step, but it's all just algebra. And keep in mind that you don't have to follow these particular steps, right? You simply have to solve for b1 however way you want to. Now, after putting the equation at the bottom to the top of the page, with a little bit more algebra, you're going to end up with the final equation at the bottom of the page that shows the final value for b1. So to sum everything up, we began with this equation for I equals 1 through n, or n equals 30 in our case, right? And we wanted to find b0 and b1 such that the sum of square prediction mistakes is minimized. After a bit of calculation, we ended up with a unique set of b0 star and b1 star, which are the ones that minimize sum of square prediction mistakes. These are the only ones, and there are no others that achieve our goal. And just to be clear, these solutions are the b0 and b1 of the fitted line that I've been talking about throughout the video. Now, in econometrics, you'll see that the notation used for these solutions are beta 0 hat and beta 1 hat. In the following videos, I'll be using these notations to refer to the intercept and slope that minimize the sum of square prediction mistakes. And in the later videos, it will be more clear why these notations are used. Also, for beta 1 hat, you may have seen a slightly different formula that looks like this. Or maybe you saw something like this. These three formulas for beta 1 hat are actually all mathematically the same. And I'll explain why we have different looking formulas in the upcoming videos. Now, using the 30 data points in our example, I've actually calculated beta 0 hat and beta 1 hat. And it is 0.42 for beta 0 hat and 0.048 for beta 1 hat. This means the equation of a fitted line that minimizes sum of square prediction mistakes is this one over here. So y values of a straight line is going to be given by 0.42 plus 0.048 times different x values. And if we plot the line on a graph along with 30 data points, this is what everything looks like. Now, I've been loosely calling this line the fitted line, but there are many other names. For example, the least squares line or ordinary least squares line, OLS line. OLS is the term used in econometrics, so that's the term I'm going to be using from now on. In econometrics, people also simply refer to the line as regression line, but I'll stick to OLS line because I think that's more technical. Now, to talk a bit more about the OLS line, when the goal is to fit a line through the data points such that the sum of square prediction mistakes is minimized, the black line, OLS line, is the only line that achieves the goal. Also, the prediction mistakes corresponding to the OLS line are called residuals. So mathematically, for I equals 1 through n, residual for student I is going to equal to yi minus a point on the OLS line corresponding to student I. And finally, we use the OLS line for various analysis, such as interpreting the estimated intercept and slope of the OLS line. And also, we can use the OLS line for predicting y values. For instance, predicting what the exam score will be given some hours of studying. I will talk about all of this more in detail in the upcoming videos. And in the next video, I will use part 3 of the video to interpret the results and also to discuss about various issues or problems with the results.